Hello, welcome back everyone. Today we're going to be starting Unit 7, which is all about vectors in physics. So today we're going to be talking about vectors as forces, and I am going to start from kind of the beginning because I know that not everybody taking the grade 12 calculus course, the MCV course, has taken physics before. Okay, some people may have, some may not have. It's not a prerequisite to this course, so a lot of this might be review for you if you've already taken the physics course. So I will be going from the beginning, as acting as though you have never done anything with vectors related to physics before, even though some people may have. Okay, so let's get going. Let's talk about this a little bit more. So here it says, vectors as forces. Force is usually associated with effort or muscular exertion, right? So, for example, lifting a book, shooting a basketball, pulling a wagon, we have to use some force, right? We've got to use some force in order to do those tasks. Here's another example. Attraction of the moon to Earth, metal to magnet, students to math, is something that either pushes or pulls an object, and it changes the uniform motion or rest of that object. So if I grab a big magnet and then, try to get little magnets to become attracted to it, there we go. There, we have our force. So force is the object's mass times the acceleration due to gravity, and units of force are measured in newtons. So F equals ma, right? M for mass, and then A for acceleration due to gravity. Now, A, acceleration due to gravity, is always 9.8 meters per second squared. Okay, so that's acceleration due to gravity, right? Because if someone is high up, right, there's always going to be some acceleration due to gravity, right? If I throw a ball at a wall or something, well, I might say, oh, it'll just go in a straight line. It'll be Pythagoras' problem. But no, it actually won't be, because there's some acceleration due to gravity that is going to impact that ball as I throw it, right? I can't just use my basic trig ratios and assume that everything's going to be okay. We'll get the correct answer, because no, we won't. We absolutely will not. So here's another example. It says a 60 kilogram person exerts a force of 60 times 9.8, or 588 newtons down on the Earth's surface, right? So for example, force in this case would be equal to ma, right? So 60 kilograms times 9.8, right? And that's going to be equal to 588, and that's going to be n, and also downwards as well, because we're going down, right? They're exerting that force down on the Earth's surface, so it's going to be downwards as well. Okay, here's a few other examples that I want to go over. We're going to start with some pretty simple examples today, because this is just an introduction to vectors as forces. So example 1 says, Bill pulls on an object with a force of 70 newtons west. So let's say here's our object, and he's going to pull 70 newtons west this way. And likewise with a force of 50 newtons west in the same direction, right? So she's going to pull with 50 newtons in the same direction, also west. Determine the resultant and equilibriant force. Okay, so let's talk about that. Well, what's our resultant force? What results from this? Well, since they're both being pulled in the same direction, it's not different directions, it's both the same direction, the resultant is going to be 120 newtons to the west, right? So very, very simple, right? Very simple. We just add 70 plus 50. Now, it would not be this if they were going in different directions. It might be something else then, but because of the same direction, we can just add their forces together and say, well, 70 newtons plus 50 newtons is 120 newtons, and there we go. Now, what about the equilibriant force? So what does the equilibriant force mean? That means the opposite force, okay? So for the equilibriant force plus the resultant force is going to be equal to 0, right? And so the equilibriant force is going to be the opposite. It's going to be 120 newtons east, right? Because let's say, for example, a very, very, very strong person pulled it the opposite direction with a force of 120 newtons to the east, right? They pulled it 120 to the opposite direction. Then both would be pulling really, really hard, but this object wouldn't move, right? What if we did 121? Then it would be moving slightly to the right. Let's say he only did 119 to the east. It'd be moving slightly to the left then, right? So it's all about the what force would neutralize this? What force would cancel out the force that we already have and make it so that the object stays still? So that's what we mean by that. Good. All right, next, let's say that Anne decides to change her direction to south. Determine the resultant and the equilibrium force. So let's do that. So over here, we're going to have 70 newtons. And then 50 newtons south, right? Because Anne switched to south. And Bill is still doing, we presume, still doing 70 to the west. And so we want to know what is our resultant force, F of R, right? Okay. So let's figure this out. How do we figure this out? Well, we've got to use Pythagoras' theorem to figure this out. So first things first, I'm going to use Pythagoras' theorem to say that the resultant force squared will be equal to 70 squared plus 50 squared, which means that the resultant force will be 86.02 once I solve for that. Now, keep in mind that the vector must have a direction as well, so I also need to find this angle, and I can find this angle using basic trig ratios. So the tangent theta is equal to the opposite, so 50 over the adjacent, which is 70, which means that theta is going to be equal to 35.54 degrees, or you could even just round up to about 36 degrees if you wanted. And so therefore, what are the resulting forces? So the resultant force is going to be equal to 86.02 newtons, and it's going to be west 35.54 degrees east. And then the equilibriant force is going to be, I keep saying that word wrong, sorry about that, it's equilibriant, I believe, not equilibriant. I'm an economics person, so my apologies for that. Anywho, this one is going to be the opposite, right? It's going to be pulling it the opposite way to make it so that that object stays still. So in that case, it's going to be 86.02 newtons east, 35.54 north, right? It's going to give us the opposite direction, right? It's going to give us this opposite angle there, right? Okay, awesome. So that's that one. All right, example 2. Actually, I encourage you to try this one on your own, or at least think about, anything like that. So this one says 3 forces of 20 newtons, 25 newtons, and 40 newtons are in a state of equilibrium, right? So the vectors all have a sum of 0. So the object is not moving, if there is an object in this example. So it says to draw a sketch of these 3 forces and determine the angle between the 2 smallest forces. So basically what they're saying here is that we have 20 and 25, kind of like this. So 25, let's make this one a little shorter and say this one is 20. And then we have our resultor like that. No, I drew this a little bit wrong. Let's draw this one like that, and then this one here, and this one is 40. So we ended up in the exact same spot, right? We forced 25 this way, 20 down, and 40, back where we started. So we end up having the sum of 0. So here's my sketch. here's my sketch of this as to what this looks like. Okay. Now, what about B? It says determine the angle between the two smallest forces. So that's basically to determine this angle here. Now, how can we do that? We're going to have to use cosine law in order to find that. So if you're unfamiliar with cosine law, make sure you go review it. I think there's grade 10 and grade 11 lecture videos on it. So I'm not going to go into detail about that. It's something we're expected to already know. But let's talk about, but I will plug in the numbers and show how to find the answer. So let's do it. So cosine of angle theta is equal to 20 squared plus 25 squared minus 40 over 2 times 20 times 25. And that's going to give us negative 575 over 1,000. And that's going to mean, let's grab a calculator here, that theta is equal to 125 degrees approximately. So there we have it. There it is. Okay, very good. So therefore, the angle between the two smallest forces is about 125 degrees. All right, so let's continue on. This next example asks, it says a 25 kilogram block lies at rest on a smooth ramp that is inclined at 40 degrees. Okay, so let's draw that. So here's our ramp. Here's our 25 kilogram item or object, whatever they want to call it, or I guess a block. And then here we have 40 degrees. It says it's inclined at 40 degrees. So now I'm actually going to draw in here our force of gravity, Fg. So Fg is equal to what? Well, Fg is going to be equal to the mass, which is 25, times the acceleration, which is 9.8 meters per second, which is going to give us 245. So there we have it. We also know that if we take the 2 here, like that, we will also have 40 degrees right here and 50 degrees right there. There we go. Awesome. Okay, good. So now what I'm going to do is I'm going to figure out what we need to figure out. So we need to figure out the forces that are parallel, which force parallel to the ramp would keep that block there, right? So here's our force of gravity. Actually, I'm going to label these a bit more clearly. Force of gravity would be this one, right? And then here's our force of B and our force of A. And the one that's parallel, or that it's supposed to be parallel, is actually, the force of A, right? So we need to figure that out, of what force B keeps it on the block. So to do that, I'm first going to say that for force A, it's going to be sine 40, which is going to be force A over 245. And that's going to be 157.48. So that's our answer to the force parallel to the ramp, right? Because this one, it's not a great drawing, but this is supposed to be parallel to this ramp. It doesn't really look like it is in my drawing there, but it is meant to be. So I'm just going to, actually, I should put some lines there to indicate that, especially because it's not the most obvious that it is. Okay, and then they also ask what force keeps the block on the ramp, and that would be the force B. So let's find force of B, same exact way. So let's find cosine of 40 equals to FB over 245, which means force B is going to be equal to 187.68. And there we have it. Very good. All right, let's do a couple other questions. Example 4 says, a mass of 20 kilograms is suspended from a ceiling by 2 lengths of rope, making angles 60 degrees and 45 degrees with the ceiling. Okay, very good. So basically we have some object, 20 kilograms that's suspended from our ceiling, right? So here's our ceiling, and we have a 60-degree angle, and we have a 45-degree angle. Okay. So here we have 60 degrees, and here we have 45 degrees, like that. And so we have our 3 forces there, and then this object is pulling down, right? So we have 3 forces, right? We have the 1 force over here, 2, and 3. 3 kind of parts to this equation. Okay, so here it says determine the tension or force applied in each rope. So first of all, let's figure out what is the tension in rope 1. Well, the tension in rope 1, in order to do that, first we've got to find the FG value, because right now we don't have any values. It's just going to be 20 times 9.8, right? Mass times acceleration, which is 196. So therefore, we can say that number 1 over sine 30, right, is going to be equal to 196 over sine 105. And we can figure out that the first force is equal to 101.46 newtons. Now, what about the second force? Well, the second force over sine 45 equals 196 over sine 105. And that's going to be equal to what? That's going to be equal to 143.48. And then we already found force 3, right? We already found that this one is going to be 196 newtons by realizing that 20 is our mass and our acceleration due to gravity is 9.8 meters per second squared. And there we have it. So all this took was a drawing and a couple times using sine law. So again, if you're unfamiliar with sine law, definitely go, make sure you go explore that, and you'll be good to go. Let's talk about the equilibrium of forces. So basically, an equilibrium of forces is when 3 forces are stable or create a triangle. So 3 forces in the state of equilibrium might look like this, right? 1, 2, 3, right? They create a triangle like this, right? And so if we have triangle ABC, and A and B are both less than C, then we would need for A plus B to be greater than C in order to be able to create a triangle, right? Because let's think about it. If we have 3 lengths of a triangle and the longest side, and the longest side is shorter than the addition of the other 2 sides, then we can't make a triangle, right? We can't make a triangle with those values. If we add the first 2 sides up and then the other one is shorter than that, right? So they can be in that state of equilibrium in only this case, right? Oh, this should have been B. My apologies. Yeah, so they can only be in a state of equilibrium in this case where A plus B if A plus B is greater than C. So let's do some examples. So can forces 15, 8, and 38 be at a state of equilibrium? Well, let's see. What's 8 plus 15? That's equal to 23. And 23 is less than 38, right? Because we need it to be true that it's greater than 23, but no, so they cannot. How about in this case? What about 6, 4, and 5? Well, let's see. 4 plus 5 equals to 9, which is greater than the third one, which is 6. And so, yes. And even if we think about, well, let's try to create a triangle, right, using 15, 8, and 38, we can't do it, whereas we can do it here, right? So it's basically all this really is this is just a fancy vector way of saying, you know, can the three sides create a triangle? And if they can, then they can be in a state of equilibrium. And if they can't, then they cannot be in a state of equilibrium. All right, well, that is it for this one. Good work, everyone. And I will see you next time when we talk about velocity and how it relates to vectors.